Hello again, welcome back. This is video lecture 9.5, part 2. We're going to focus on the reading in chapter 9, section 8, and we're going to talk about collisions, more collisions, but now collisions in which there is two-dimensional motion. Motion in a plane, not just along one line. Okay, we're not going to introduce any new ideas here, no new physics. It's just going to be a little bit more math. So here's the kind of basic scenario, and my big tip throughout all of this is to remember that linear momentum is a vector with components, and we must work separately with x and y components. That's the key thing to remember. Okay, the schematic picture here on the left is an overhead view of an xy coordinate system, two particles. Particle 1 and particle 2, mass m1, mass m2. If you want to use the same kind of language as we did in the previous part of this video lecture, particle 1 is initially moving in, that's the projectile. It's coming in right here, from our left going towards our right, towards the origin. Particle 2 is the target. And just to make the math a little bit less cumbersome, we're going to pretty much always, well, almost always, take the target to be at rest initially. So you can see particle 2 is just sitting there at rest at the origin. This is an initial picture. And you can see that particle 1 is moving with a velocity v1 initial, right there. And that velocity happens to be, according to this picture, along one of the coordinate axes, plus x. That's just a nice way to set it up. That way, you know, initially you have only x momentum. Okay, then it also is trying to show in one picture what's happening after the collision. So particle 1 comes in along that blue straight line, and now we have a collision between 1 and 2. Imagine like two air pucks on an air table, but it's not exactly head-on. It's more of a glancing blow, so that when they interact with each other, then the motions go off at angles relative to the x-axis. Particle 1, after the collision, it comes in like so, straight line. Then the collision happens, boom, and then it travels along that line right there. And then this right here shows particle 1, the same particle 1 we started with, but now that's what it's doing after the collision. And so this arrow right here represents the final velocity of particle 1, v1 final. Particle 2, of course, was initially at rest. Because of this off-center collision with particle 1, it goes off in that direction after the collision. So that's now particle 2 a little bit after the collision. And there is its velocity vector afterwards, v2 final. And those velocity vectors make angles that are important to keep track of relative to plus x. Theta 2 is the angle that path for particle 2 makes relative to plus x. It's also the angle for v2 final relative to plus x. And theta 1 is really measured there relative to the incoming direction. There's theta 1. That's the angle of v1 final relative to plus x. We won't do any negative angles, by the way. We just want the size of those angles. Okay, so I just want to make sure that you understand what picture we're envisioning here. But like I said, there's no new physics. It's a collision. The system is the two things that collide. The key physics is that the linear momentum of this system is conserved. That's the physics. And we just apply it now. So I've started by writing that idea with symbols. Big P1 initial plus big P2 initial must equal big P1 final plus big P2 final. Big P, because it's a system of more than one particle. It's two particles. Arrows on top of all the capital P's because linear momentum is a vector. Now, of course, momentum for a particle is mass times velocity vector. So here's another way to write that. m1 v1 initial arrow plus m2 v2 initial arrow equals m1 v1 final arrow plus m2 v2 final arrow. All these are vectors, though. So what we really have to do is deal separately with the x and y components. So that's why I've drawn off two lines going off from there, because there's really two equations there. One where all the velocities are x components, and a separate equation where all the velocities are y components. So let me note those. First, x components. m1 times v1 initial x plus m2 times v2 initial x. Just take the x components of the velocities. Must equal m1 v1 final x plus m2 v2 final x. That gives us one equation. Could even number it. Equation 1. Separately, m1 v1 initial y plus m2 v2 initial y must equal m1 v1 final y plus m2 v2 final y. And that gives us another equation. Let's call it 2. Those equations must be satisfied. The motion that we will see of these particles is constrained so as to satisfy those two. We know that from many, many, many experiments. So those two equations, 1 and 2, must be valid. Now the next thing I'm going to talk about is conditional. It might be true and it might not. It's case dependent. And that statement is about whether or not the collision is elastic. We will usually end up just being told if it's elastic or not, usually. If we know the collision is elastic, then we can add another equation constraining the motion. Namely, the total kinetic energy before the collision must equal the total kinetic energy after. K1 initial plus K2 initial must equal K1 final plus K2 final. Or 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared must equal 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. Please note, any of those v squareds, I'll write it out for v1 initial, but it's true for all the v's you see in this equation. It really means v1 initial x component squared plus v1 initial y component squared. That's what this symbol means, because it's the magnitude of the velocity squared. That means you got to include x component squared plus y component squared, Pythagorean theorem. So watch out for that. If it is valid, I'll call it equation 3, and I'll put beside it conditional. It might be valid if we know that the collision is elastic. Okay, let's just go straight to practice. That's all I'm going to do for the rest of this video. Let's do some practice with a two-dimensional collision. I'm going to use a Wiley Plus animation with this practice. Okay, here's the situation. The animation I'm going to show you provides an overhead view of a horizontal, frictionless XY coordinate system on which two particles can move, like the picture I just showed you. Initially, particle 2 is at rest just to one side of the origin, with its center on the y-axis. And particle 2 travels at 2 meters per second in the plus x direction. The resulting collision between the particles is not a head-on collision, and after the collision, the two particles travel in different directions. Run the animation. Well, then maybe we should do that. So let me go over to Wiley Plus. Now there's the picture. You're looking at the XY coordinate system from above. Particle 1 is the red disk. Think of like an air puck on an air table. Perfectly frictionless air table. Particle 2 is the blue disk, initially at rest, just a little off from the origin. Okay? And we're just going to run the animation. You can see particle 1 has an initial momentum. See that orange or gold arrow there? It's labeled, if you mouse over it, P1. Okay? All right, and now I'm going to run the animation. And they come in, and they collide, and then they go off, and there's an angle theta 1 for the direction of particle 1's travel after the collision, and theta 2 for the direction of particle 2's travel. All right, go back. I'm going to be going back and forth between the animation and the wording. It says, the initial location of particle 2 can be varied by changing the value of the parameter theta 2, which in turn determines the angle at which the blue particle moves relative to the plus x direction after the collision. By default, theta 2 equals 45 degrees. And you can see up at the top, the middle slider, theta 2 in degrees, is set for 45. So that's why the angle theta 2 for particle 2 going off into the first quadrant is at 45 degrees with the plus x direction. Okay? All right, that is a two-dimensional collision because it's not head-on. It's a little off-center. And here come the questions. We'll answer them one by one. We take the system to consist of the two particles that collide. Of course, that's what you pick when you have a collision. Let's take the mass of each particle to be 1.113 kilograms. Aha, they have equal masses. That's important. We are to find the values of the following quantities. Capital P initial x, capital P initial y, capital P final x, capital P final y. Okay, here we go. Let's start with capital P initial x. Might be helpful to be reminded of what's happening in the initial situation. Let me drag the time slider back to before the collision, like that. Okay? Particle 2, that's the one in blue, is at rest. It has no momentum whatsoever. Particle 1 is traveling with a velocity in the plus x direction, so it has an x momentum, mass times that velocity right there. Okay, now, one of the things I perhaps didn't say, but I guess I better say, is the wording up there tells me that particle 1 travels at 2 meters per second in the plus x direction. So now I can write down capital P initial x. It's the mass of, I'll write it as m1, because I want to remember I'm dealing with 1, but they both have the same mass, times the entire magnitude of v1 initial, because that entire initial velocity for 1 is in the x direction. So the masses of both are 0.113 kilograms, and the magnitude of the initial velocity for particle 1 is 2 meters per second, and so you get positive 0.226 kilogram times meter per second. That's P initial x. All right, what is P initial y, the initial y momentum of the system before the collision? I'd like you to answer that for yourself. Feel free to pause the video if you so desire. So did you remember in the animation that before the collision, particle 2 is not moving at all, and particle 1 is moving purely in the plus x direction? There is no velocity component in the y direction, so there is no y component of the initial momentum. P initial y is 0. Okay? Purely by observation from the animation. Next, what is capital P final x? Here, I just invoke conservation of linear momentum. So P final x must equal P initial x. That's what conservation of linear momentum means. By components, the initial x momentum and the final x momentum are equal. So, the final x momentum is exactly the value I had for the initial x momentum, 0.226 kilogram meter per second. Similarly, P final y component must equal P initial y component. Again, conservation of linear momentum. So the final y momentum equals the initial y momentum, but the initial y momentum was 0. So the final y momentum is 0. Even though after the motion, after the collision, I should say, both particles are moving, and they're moving off at angles relative to plus x. So they both have y momenta. But the total y momentum of the system has got to be 0. That's a severe constraint on the motion, as we will see. Okay, but we have answered question 1 in the practice. So let's go on to question 2. After the collision, it is observed that the red particle's direction of motion makes an angle of theta 1 equal to 45 degrees below the plus x axis. The red particle is particle 1. What is the magnitude of each particle's velocity after the collision? So, magnitude of velocity. How fast is each particle moving? Particle 1, the red one. Particle 2, the blue one. Let me get myself some space because I'm going to want to draw a little bit here. I know we have the animation, but I'm going to draw my own sketch of post-collision. What's going on after the collision? So we have our XY coordinate system, our axes labeled. The collision happened basically in the vicinity of the origin. Afterwards, particle 2, the blue one, has a velocity v2 final, like so, at an angle 45 degrees to plus x. I know that from the animation. I'm told in part 2 that particle 1 goes off. It's a red disk, so I'm going to draw it in red, with a velocity v1 final that makes an angle of 45 degrees below the plus x axis. So there's my sketch of what's happening after the collision. Particle 2's gone off into quadrant 1. Particle 1's gone off into quadrant 4. But they both go off at a 45-degree angle to plus x. I want the magnitude of v1 final and the magnitude of v2 final. How will I find it? I'm going to use conservation of linear momentum. And probably the easier component, because you've got to do both components, the easier component to work with, at least initially, is the y component. Because it must be true, I've already determined, that the final y momentum of the system must equal 0. Even though both particles have a y component to their velocity. I'll sketch the components of their velocities there. And v2 final has a y component, and v1 final has a y component. So particle 2 has a y momentum, and particle 1 has a y momentum. But the total y momentum must equal 0. How are we going to express these y momenta for the two particles? I'll do particle 1 first, but note the y velocity for particle 1, I just shaded it right there in yellow, is pointing in the negative y direction. So the y velocity of particle 1 is negative, so the y momentum of particle 1 is negative. And that y velocity is magnitude v1 times, this angle right here is 45, times sine of 45. So is this angle 45. So we're going to have, I'm just going to write minus m, magnitude of v1 final, sine 45 degrees. That's the y momentum for particle 1 after the collision. It's just m times vy. And vy is negative magnitude v1 final sine 45. Now the y momentum for particle 2 is definitely positive because the y velocity for particle 2 is positive. there's the y velocity for particle 2 right there. And that y velocity is magnitude v2 final times sine of 45. So the y momentum will be m magnitude v2 final sine 45. And there are the two y momenta. They must total to 0. What do I learn from this weird-looking equation? I can write it like this. M magnitude v1 final sine 45 must equal m magnitude v2 final sine 45. Yes, just from algebra. I can divide both sides by m. I can divide both sides by sine 45. And what I've discovered is that since the particles have equal mass and go off at equal angles, they also must have equal final speeds. Speeds, not velocities, because they're going off in different directions. But the magnitudes of those velocities are equal. Let's just call that then VF with no other notation for that equal final speed. Okay, now I haven't answered the question yet entirely. I've just proved that they have the same speed after the collision. I still need to find out what that speed is. How will I do that? Well, the physics idea I've used so far is conservation of linear momentum for the y component. I haven't used the x component yet. That has to be, for momentum, that has to be conserved too. So now I will use what I already learned, that P final x must equal P initial x, which is positive 0.226 kilogram meter per second. All right, so here we go. We're going to require P final x equal that. Where do I get the P final x for the system? Well, both particles have velocities with x components, so both particles have an x momentum after the collision. That will be m times the magnitude of the final velocity times cosine 45. Because now I need to take the x component of the velocity, like that one, and that one right there, which is magnitude v cosine 45, and then multiply by m. But it'll be exactly the same x component exactly for each, right? For each particle. So it's just 2 times that expression. That's the total x momentum after the collision. So that must equal 0.226 kilogram meter per second. So let's just solve for v. 0.226 kilogram meter per second over m times cosine of 45 degrees. So 0.226 kilogram meter per second over m whoops, I can't lose that 2, can I? That's important. That's important. Times, for the mass, 0.113 kilograms times the cosine of 45 degrees. And you just put that in your calculator. 1.414 meters per second. Looks like the decimal approximation to square root of 2. Doesn't it? But anyways, that's the answer for question 2. That is the speed of each particle after the collision. I used conservation of linear momentum, both for y components and for x components. Everything's by components. Okay, let's go on to question 3. Based on the answers to questions 1 and 2, is the collision between the two particles elastic? Answer yes or no. Justify with a calculation. Yeah, you can't just take a 50-50 guess and then, if you're right, say hurrah, because that doesn't show any understanding of physics. So, how are we going to justify, how are we going to determine whether the collision is elastic or not? It's not going to tell me. Remember what elastic means. If it is elastic, The total kinetic energy before the collision must equal the total kinetic energy after the collision. So you know what I'm going to do? I'm going to calculate the ratio of K total final to K total initial and see if that ratio equals 1. If that ratio equals 1, those kinetic energies are equal, the collision is elastic. That's simple. If the ratio is not 1, it's not elastic, it's inelastic. All right, this calculation is actually not as hard as you might think it originally. Think about the denominator first, K total initial. Think back, before the collision, particle 2 was at rest, no kinetic energy at all. Particle 1 was moving, so it has kinetic energy. Remember the formula, 1/2 m magnitude of velocity squared. So magnitude of V1 initial squared. That's a symbolic expression for K total initial. Now let's think about K total final. Okay, after the collision, they're both moving. Particle 1's moving up into the first quadrant at 45 degrees to the x-axis. Particle 2's moving into the fourth quadrant at 45 degrees. So they're both moving, they both contribute to the kinetic energy, but they have the same speed, same magnitude of velocity, and they have the same mass. So all I have to do to get the total kinetic energy afterwards is take the kinetic energy of one of them, 1/2 mv squared, and multiply by 2, because they both have the same kinetic energy. Where that V I wrote in the numerator is the answer I just found in question 3, right there. At 1.414 meters per second. Now note, by the way, there's a 1/2 upstairs and a 1/2 downstairs. So this expression, oh, and the m's cancel, of course. So this expression really is 2V final squared over the magnitude of V1 initial squared. That's 2 times 1.414 meters per second squared over 2 meters per second squared. Notice the units cancel, the ratio is dimensionless. You check that on your calculator, but you will see that it is 1. That tells me that the collision is elastic. It's a 2-dimensional elastic collision. Not only is linear momentum x and linear momentum y conserved, or are they conserved, but also the total kinetic energy is conserved. All right, now, one more question. Question 4. Go back to the animation and reset it. Using the slider, adjust the angle θ2 so that it is θ2 equals 60 degrees. That means particle 2 is going to go off at 60 degrees now to the plus x direction. Keep the mass of particle 2 the same as the mass of particle 1. Run the animation again. Okay, we will do that. Suppose that observation determines that the speed of particle 2 after the collision is 1 meter per second. Speed. What is the direction of travel θ1 of particle 1 after the collision? You may assume that the angle is measured clockwise in the plus x-axis, but we'll record the answer as a positive value. All right, so if we go to the animation, I will reset it. I will now put θ2 to 60. Okay, so now particle 2, the blue particle, is going to go off at 60 degrees to plus x. I wonder what angle particle 1 is going to go off at. Want to take a guess? Here we go. Well, it isn't going to tell us the number, is it? But look at the angle between the blue and the red lines after the collision. What does that look like to you? Does it look like a right angle? Does it look like θ1 plus θ2 equals 90? I could even adjust θ2 in the slider here. And it looks like theta 1 plus theta 2 is equal to 90, no matter what we put for theta 2, as long as the masses are equal and the collision is elastic. So we might guess then that if theta 2 is 60, theta 1 is 30. And that, it turns out, would be a very good guess. But let's go ahead and show it. Okay. All right. So our guess, theta 1 equals 30. But we'll show it by requiring that the total y momentum be 0 and the total x momentum be 0.226 kilogram meter per second. So, particle 1 and particle 2. Particle 2 has the positive y momentum. It will be m v2 final sine 60. And particle 1 will have negative y momentum, m v1 final sine theta 1. I'm guessing theta 1's 30, but I don't know. And that total must equal 0. Let me divide by m, so that goes away. And let me just rearrange and write this as v2 final times sine 60 must equal magnitude v1 final sine theta 1. And I will remind you that we are told that after the collision, the speed of particle 2 is 1 meter per second. So that's that magnitude. The problem with this equation, which I will number equation 1, is that it has two unknowns. I don't know the speed of particle 1 after the collision, v1 final magnitude, and I don't know the angle, theta 1. So two unknowns in one equation, not enough equations. I need another equation. Comes from the x momentum. P final x must equal 0.226. All right, let's add them up. For particle 2, the x momentum is m, v2 final magnitude cosine 60 plus positive m v1 final cosine theta 1 must equal 0.226 kilogram meter per second. Let me divide both sides by m and rearrange so that I get v1 final times cosine theta 1 alone by itself. I will drop the units here for a moment. I just won't write them. So I have 0.226 over m, watch your algebra here, minus magnitude v2 final cosine 60. That's my second equation. Okay? All right, now, if you need to pause the video, think this out for yourself, that's perfectly appropriate. But it is important that you understand how I got these two equations and that you would be able to do it for yourself. Now, this formula has the same two unknowns, formula equation 2, v1 final magnitude and theta 1. So I have two equations and two unknowns. I solve for the one I want, which is theta 1. There's a number of ways to think about how you're going to do that, but it is at the end of the day just algebra. I'm going to divide equation 1 by equation 2. You divide left side by left side and right side by right side. When I do that, well, I should have written them. Well, yeah. So the v1 final magnitudes cancel, and on one side I have tan theta 1. On the other side I have v2 final magnitude sine 60 over 0.226 over m minus v2 magnitude cosine 60. And now you plug in numbers. v2 final magnitude, 1 meter per second. Mass, 0.113 kilograms. Remember, the 0.226 is in unit of kilogram meter per second. V2 final magnitude, 1 meter per second. Do that very carefully on your calculator, and you end up getting, in the numerator, square root of 3 over 2, and in the denominator, 1.5, or 3/2, which means that this is really the square root of 3 over 3. And that's what tan theta 1 must equal. So theta 1 is the inverse tangent of square root of 3 over 3. You put that in your calculator in degree mode. Sure enough, it's 30 degrees. Okay? By the way, it didn't ask this, but we can also find now the magnitude of V1 final, i.e. the speed of particle 1 after the collision. Just use equation 1 and solve for V1 final. V2 final sine 60 over sine 30, because I now know theta 1 is 30. And I get 1.73 meters per second. That's how fast particle 1 goes off. So they don't go off at the same speed this time. But they do go off at angles that add up to 90. I want to show you that with a little video that Professor Storms and I made on the air table with the air pucks, like I showed you in an earlier video, with magnetic air pucks. So they will collide off each other by a magnetic repulsion. It will be approximately elastic. They have approximately equal mass, but that won't be a head-on collision. It'll be a glancing collision, so they'll go off at angles. And let's see if the two angles add up to 90. So if we can just see that. Okay, let's see if I can run that now. If right now it's be a dark screen, perfectly elastic collision between objects of equal mass. We'll do it in slow-mo. Glancing, there they go, off at different angles. There is a representation of the linear momentum vectors, before and after. And there is showing the angles that they go off at. One's called theta, one's called phi. And you can see, you can add up those angles and you'll find that they're very close to 90 degrees. They're within a couple of degrees. And that's not bad for actual physical setup. Okay? So, elastic collision in 2 dimensions with equal masses, they will fly off and their angles will add up to 90 degrees to each other. Okay, so there's just one more thing to mention for this video lecture. No, I take it back. There isn't. I thought I had a class engagement exercise here, but I do not. So, we will be talking in class about 2-dimensional collisions, but that's all for this video.